It works. Okay, well, welcome everybody to session A2, Energy Systems. So we have a bit of a change to the published programme. We originally had 4 speakers going to be talking in this session. Unfortunately, we only have 2 now because 2 have pulled out. So Tesfu Gebremedin, who's going to be talking about system modelling and stability, is a late cancellation, and also Veronica Tadrak, who pulled out previously. So we have 2 speakers this morning. Orestes Angelidis from the University of Glasgow, who's going to be talking about district heating and cooling with decentralised energy substations, opportunities and barriers for holistic energy system decarbonisation, and that will be followed by Emily Chapman from the University of Strathclyde, who's going to be talking about the value of offshore wind-derived hydrogen to the Scottish energy system. I'll just quickly introduce myself. I'm your chair. So my name is Nick Kelly from the University of Strathclyde. I'm based in mechanical and aerospace engineering, and I'm the ETP board member for Strathclyde University. So without further ado, I'll invite Orestes to give his presentation.
Good morning, everyone. Can you hear me well? Yeah, I guess you can. Ideal. So this is an awfully long title, but it still is interesting. I'll try my best to keep you as engaged as possible. I will put a timer to make sure I keep on track with time, despite having more time, but more time for questions, I guess, afterwards. So my name is Orestes, and I'm with the University of Glasgow and the University of Edinburgh. The industrial partner is Ramble, which is an engineering consultancy. What I will be talking to you today is about district heating and cooling, which is an industry energy system in a way, because we're just talking about the whole heat network. And what we will be looking in more specifically, it's about the opportunities and barriers for a holistic energy system for decarbonization. We will be going through my research, the background, a bit on the literature review that I've been doing, and then dive in some of the modeling and the summary of it all. At any point, if you have any questions, keep them, and we'll have some time at the very end to address all questions. As I understand, this is a digital conference as well, so if you have any questions, you can just put them in the chat, and hopefully we can see them afterwards. So, to get it started, my research in a few words, what I'm looking into is the decarbonization of heating and cooling. I'm looking into the holistic aspect of that system. What that means is, how do we couple the heating and cooling with the electricity grid? If you were in the previous panel, they mentioned heat pumps, so inherently we have a link with the electricity grid, but how can we make it so that the two couples are working in synergy rather than one is built on top of the other, and we need to put a lot more infrastructure for renewable energy. The stakeholders you can see at the bottom of the screen is quite a few, so that means I have a lot of a lot of stakeholders to please, but thankfully everything has been going well so far. At the moment, I just want to paint the picture in terms of what's happening at the moment. So we are relying heavily on electricity grid decarbonization. Other than fossil fuels, that's our only way of trying and heating and cooling through heat pumps or electric boilers, electric chillers, in order to achieve heating and cooling in both residential, commercial, and industrial uses. There's 3 main, let's say, levels at the moment that we're looking for heating and cooling. It's the individual solution, so that might be direct electric heating, that might be individual air source heat pumps that you find them a lot in kind of hotter climates, that you just have air conditioning units. And then we go into more plant room level solutions. So that might be if you have an apartment block where you would just have a centralized heat pump or boiler or CHP sending through a riser hot water to each individual flat for both hot water and heating. And then we have the final step, which has been around since late 1800s in the US, and it got more popular in Denmark and the Scandinavian countries around the 70s with the oil crisis, which is district heating. So you have one centralized plant sending hot water through a network of pipes to buildings for both residential and commercial use. Now, what I want to talk to you today is about, one would say, next step, a step sideways, a step backwards, depends on who you ask. But the concept is that we have one network that it's on ambient temperature that supplies both heating and cooling. So as we see a rise in cooling needs, and we have a scattered waste heat opportunities throughout our cities, that could be a way to actually harness them. When we have heating and cooling, essentially, well, cooling is the waste output from cooling is heating, so that could be used further down the line. So let's say if we have a supermarket that needs to use some cooling, that could be used to power your hot shower further down in the line. Obviously, there's a lot more intricacies with this, but that's the main concept about how we have a more circular approach to how we use our energy system. We use decentralized energy substations that depend on what thermal zoning we have. So it could just be supplying one flat, or it could be supplying a whole district with different temperature needs. That gives us flexibility, and it allows us to have to meet different temperature needs within a district. Hopefully that makes sense. But one problem that arises is that we have high seasonality of demand. So here I am speaking and saying we can match the two, heating and cooling, but in reality we have, well, mainly heating for winter and mainly cooling for summer. So how do we transpose the two? How do we take use of co-occurrence? And that's where a lot of balancing units can come into play, where we can have an active balancing unit in terms of a heat pump, or a passive balancing unit, which would be a thermal energy storage system, and usually that would be a seasonal thermal energy storage system, which could be an aquifer, where it has a hot and cold well, where essentially we can just shift that profile and use it during the winter or during the summer. Obviously, there's a lot of issues with this as well, but this is an idea on how we can start putting that simultaneous aspect more and more. All right, so let's take a first break and dive into more of the technical aspects. I'm not running out of time, which is lovely. And let's see some of the outputs from the literature review first. So the way I tried to tackle this was to identify what are the key parameters, to just have the whole story. So when we're looking at the system, the first thing to see is how does it compare to conventional system. That would be the three levels that we saw initially: individual, plant room, and centralized level. Then once we kind of see what the differences are there, we start looking into the physics of operation, of how does this system actually work, how can we actually implement this. Once we get a sense of that, then we start going into how does the whole thermal grid as a solution act as a flexibility element to the electricity grid. Does it, or does it act as an extra strain because we have more decentralized solutions? And how does the role of the thermal energy storage come into play in terms of the seasonality of it and the daily thermal energy storage in more of a kind of plant room level? And finally, to tie all these components up, we have what a new business model do we have to actually capture all the characteristics of the system and make sure that we're making the most out of it. Now, to approach it, I took two approaches. One was to just do a systematic literature review, so see what's out there from published papers to documents from institutions from throughout the world. But that still left quite a lot of questions unanswered, because this is a new technology of about 4 to 5 years. And after discussions with colleagues in both Denmark and the UK, I got very opposing opinions on it. Some were saying that that's the future, while others were saying that that's an absolutely stupid idea, it makes no sense. So I engaged into some stakeholder interviews to try and get their ideas in terms of what they think, try to get some qualitative answers, and just let them properly express their feelings on all these 5 sectors. And that advised a literature review, which at the moment is under review, so hopefully when the paper is out you can all read it. But the key outputs were that high seasonal co-occurrence is essential to the system's economic performance. We could shift it through a thermal energy storage, but this is essential for it to be economically viable. Secondly, having a low number of prosumers, a low number of points of connections is also important for hydraulic and control complexities that we try to limit in terms of bidirectionality of flow and control of all the individual heat pumps. Novel mechanisms on both the business model and the asset ownership are also being investigated but are not clear, and there's a very big lack of legal framework as to where these networks could be implemented. So overall, the system needs to be seen as a step sideways, I would say, rather than forwards or backwards. It's a tool in our arsenal of decarbonization, rather than saying it should always be the solution or it should never be the solution. So what is important is to actually see which areas and in which cases is a beneficial aspect of operation. In order to do this, we really need to capture the system. Now, in contrast to more conventional system, it's a lot more complex because we're doing both heating and cooling. We have bidirectionality of mass and energy. So in order, there's not a pointer here, no. But in order to see how much of that supermarket's cooling could be used further down the line from some of these houses, we need to have an hour-by-hour simulation that can capture both thermofluid, so both hydraulic and energy flows. So it becomes a lot more complicated. So in order to do this, we need a quite sophisticated simulation model. And at the same time, we have to model the alternatives, which would be captured in a techno-economic model, which, because we need to compare a lot of scenarios, need to happen as quickly as possible. So in order to do this, there's two parts to my modeling. One is to do the detailed simulation model in Modelica. It's the language that I've been using, which is awfully difficult to use. I would advise you not to use it. But it can capture a lot of these aspects. And it is an object-oriented modeling approach, which is acausal, so we can have based on mathematical equations. And we can use it as Lego pieces developed by a lot of institutions that we can just collect and build our own models. And on the other hand, we have a techno-economic model that I have been building, which takes all of the aspects of a system design and through some, I wouldn't say that fancy, but algorithms kind of makes the whole process go as quickly as possible. So when I click a button, it takes about 10 seconds to size the whole network and give us an output in terms of the techno-economic performance. So these are some of the key aspects that I was talking about in terms of the Lego pieces and in terms of the techno-economic model that ties all things together. So, perfect. I just want to summarize everything into these three components that we have discussed. So phase one was the literature review with some of the qualitative opportunities and barriers that we're seeing, that we touched on. The second one is what would be the design methodology to capture the alternatives and actually feed the outputs from a simulation model to start seeing in which cases the system is performing better than the others. And finally, this detailed modeling to capture all the hydraulic and energy sub-cycles that we're seeing. These are some of the references. And thank you very much for your time. I think that covers everything. Yeah, I think questions will be either now or at the end. Is it now? Perfect.
Okay, so we're going to have questions at the end, so if you can just save them up for each of the speakers. We're also going to have a roving mic around as well, so if you could just hold off on the questions until you have the mic in your hand. We need to capture your question for posterity. So next up is Emily. So Emily, you're going to be talking about hydrogen and its integration into the electricity network, or how it helps us with the operation of the network. So over to you.
Hello. So I am just finishing my first year of doing my PhD. So any really technical questions, I would advise you to go back and talk to Kirsty, because she had a very nice presentation this morning. And a lot of what she talked about in terms of hydrogen and offshore wind is what I'm looking at. So she's kind of spoiled most of my presentation for all of you, which is lovely for me. So I'm looking at offshore wind generated hydrogen and its value to energy security in Scotland. So the four main points towards energy security are affordability. Is energy affordable? Accessibility. Can everybody that needs energy access energy when they need it? Which is another part of availability. Is it available when it's needed? And the last part is acceptability. So in terms of renewable energy, a lot of people, that's acceptable, perfectly acceptable, it's nice. But when you think of, say, hydrogen, do people know what hydrogen is? How can we make sure that people aren't just going to assume that we're talking about explosives, for example? So in terms of the Scottish Government, they've got some nice lofty aspirations for us, as Kirsty mentioned this morning, the ScotWind, up to 30 gigawatts of energy potential, and they're hoping for 5 gigawatts of hydrogen by 2035, which is lovely for me. So these are the research questions that I'm looking at, and it's a strange area to be researching because I am basically modeling the future of energy. So I'm trying to determine if in the future we use hydrogen, is it worthwhile? What usage of hydrogen is going to be worthwhile because they're apparently very set on using it. So my methodology is I'm using a very lovely simulation tool that is called Calliope. It is an energy system modeling tool that focuses on systems that have high shares of renewables in it. So it's a lot of nice Python coding work. I don't know if any of you use Python. I didn't before I started my PhD, so I've had a very fun time of learning how to use it, and whether or not I'm doing it entirely correctly is yet to be seen, but that's another matter entirely. In terms of the energy system model, we're basically modeling an energy system, which it sounds stupid, but I have to reiterate it because I didn't quite understand exactly what I was doing when I started. I'm basically taking pre-existing data that I've got from the national grid, and I am scaling it up to the future potential energy that we have in Scotland. So I have the data from last year, and I've cut it down to just be Scotland, and just be the wind output from Scotland and the demand for Scotland. And I'm turning those into capacity factors and then scaling them up to if we had 30 gigawatts of wind in Scotland to determine if we used excess wind energy, how much hydrogen could we get from that, and how much storage would we need. That's another big part of my entire project. At the moment, this is in proof of concept stage, so it's not linking locations. I'm just treating Scotland as a blob at the moment. So it's not connecting where energy is produced with where energy could be stored, none of that just yet. It will be in the future though, so that's something to look forward to. I started out using natural gas in gas turbines, just to make sure that the model was working, and then we switched it over to hydrogen. So this is a very interesting graph of projected wind capacity compared to projected demand for Scotland. So 4 gigawatts even of projected demand, and that's the black line on this very nicely blurry graph at the top. So as you can see, the 30 gigawatts of wind that we could have, even though it's miles above the demand that we actually need, there are sections where it's below the line. So energy wouldn't be secure during those times if only wind energy was used. This is the absolutely horrific graph that I get when I run my simulation. So to explain it a little bit, the nice black line that runs straight through the middle of it is the demand line. That is the fluctuations, and this is it's scaled up to 30 gigawatts. So it's a theoretical year when we have 30 gigawatts of capacity. So the demand line runs right through the middle, and it's a little bit difficult to understand what's going on in this. So to explain, the blue lines that are coming down and the orange lines that are going up, as you can see, they kind of correlate directly. That's basically the simulation decides itself when it's necessary for offshore wind, when it's producing more than demand, to turn it into hydrogen using an electrolyzer. And then the orange sections are when the hydrogen that it's made using the electrolyzer is being put back into the system through the use of hydrogen gas turbines. So to give you a little bit of a closer view of some areas, this is the April section. And as you can see, there is still a little area that would require import, which is what I'm looking at. I need to know how much hydrogen storage would be necessary to ensure that we aren't relying on imports and that hydrogen is a feasible option for use in ancillary services. So I do have a few more examples of those. So June, there's significantly less import, and the offshore wind energy is meeting demand most of the time. Again, in October, there is a very, very tiny amount of import. So theoretically, the idea behind all this is that using hydrogen storage and using hydrogen that is made from offshore wind in that hydrogen storage can provide backup energy when wind isn't producing enough to meet demand. Okay, so that's going on to future stuff. I'm going to be connecting it to grid space points so that I can map where we have electricity that would be coming in and where potential hydrogen stores will be. That is another part of my project that I haven't got into yet, because as I said, I'm just finishing my first year, and I started in chemical engineering, not electrical engineering. So I'm learning all of this, as you all are. So it's looking promising, but again, this is energy simulation, and if you know anything about energy simulation, is that if you don't put the right stuff in to start with, you don't get any relevant answers. So it's a lot of referencing and making sure that I'm using figures that are correct and are going to add up in the end. So that's me.
So Emily is going to stay up. I can ask Orestes to come up and have a seat as well, and we can open the floor to questions once we have the roving mic. So that should be around. Oh, you've got it here. Okay, that's great, Chris. So, and the mics on the desk are on. They're okay. Good. Okay, so that was two very interesting, slightly different presentations. So one was looking at fourth or fifth generation district heating. The other one was looking at how we can use hydrogen within a potential future energy system. So lots of food for thought, and I'm sure there's plenty of questions. So have we got some questions from the floor? Yep. Okay. So if you can just state your name and affiliation as well as your question.
Hi, I'm Leslie from Heriot-Watt University. Just a question for the first speaker. The modelling that you're doing, is that based on a specific location, or is that all sort of hypothetical locations that you're working on?
So the idea is to have a global model that could be used for anything, but the development process I'm using a case study, and that is Clyde Gateway, which is down in Glasgow. And there are ideas to actually run some hardware in the loop, so have a digital twin of the model along with an actual lab and Technical University of Munich to actually observe some of these hydraulic subcycles and validate the model so that we can have more realistic results. Thank you. Okay, so we had another question over here as well. Again, if you can just see your name and affiliation.
So my name is Mohamed Numair. I'm a PhD student at Glasgow Caledonian University. And my question is to Emily's research. I really like the topic that we can use the extra power from renewables, such as wind, to store it into hydrogen, because batteries storage efficiency are not that good now. They are improving, and also because the cost of it. But from the graph, I saw that you invested a lot of extra power from the winds into electrolyzer, but when it came to demand, you still couldn't, it showed that we couldn't meet the demand and we needed some import. So do you have a figure on the efficiency of conversion from hydrogen back to electricity and from the extra power from wind to hydrogen? Do we have a figure of the efficiency value?
Not at the moment, because it's still just a proof of concept kind of area. A lot of the efficiencies are kind of assumed. So the storage itself, I'm looking at salt caverns. My secondary supervisor is Katrina Edelman, who works at Glasgow University, and that's her research area. So it's one of those things that I haven't got fully into yet, but that is something that I will be looking at in the future, yeah.
Okay, so do we have any more questions on both of these topics? I've got plenty, so don't worry. Okay, so again, so if we can have a quick question from you, thanks, and then there's a couple more hands went up on the floor
just
there as
for
well.
Emily, your graph that showed the wind generation, is that all based on assuming that wind farms in one location, or are they kind of dotted all around the coast?
At the minute, it's a copper plate model, so it's not assigning locations to anything, it's just assuming total capacity.
Okay, so there's a couple of hands went up briefly there as well, so I'm assuming there's some. Yep, gentleman at the front here. So again, if you can give your name and affiliation, please.
So Antoine Reglis from Napier University. One question for Orestes. The access to data, how do you find it? Do you rely on data easily accessible for your modeling, and then do you forecast any issue for developing this approach? And so access to data would be necessary for hydraulic, I guess, and also energy use.
Yeah, thank you for your question. And it's a really good one, because this is really addressing one of the key issues at the moment on the field, which is the fact that there's a shortage of data, both in terms of models to be used and in terms of outputs. So the good thing with Modelica, despite it being quite a tricky language to actually use, is the fact that it's open source, and it has also open source software environment to actually run the language. So there's a lot of universities throughout the world, and more specifically the Berkeley Lab, Aachen University, TU Munich, and I think Lund University are the key ones that have published some these Lego pieces, let's call them, so that components that can be used in this object-oriented language. So there is some availability that I am using at the moment, and that it's very welcome. And I think the key aspect is to have everything open access, so the outputs of my research, both that techno-economic model that I mentioned, along with the simulation model, they are going to be open access on GitHub.
Okay. Any more questions from the floor? Yep.
Hello, Alistair MacDonald from Edinburgh University. A question for you, Emily, and first of all, well done for moving from chemical engineering into something a bit more electrical. It was really interesting that you were presenting some very early results, and I appreciate that when I asked the question. Do you get a sense for how much hydrogen you could produce and how much is ending up going back into electricity? Is there more hydrogen that you're assuming is going to be used for other purposes? And can you give us a gut feel? Is it like 50-50, 10-90? You know, how much excess hydrogen beyond the electricity system?
Yeah, I can't really give you any numbers at the minute. I wouldn't know those off the top of my head to start with. But my project is mainly just focusing on using hydrogen for like ancillary services. It's not accounting for like transportation or going to homes or stuff. It's a little bit too broad for the kind of research that I'm looking at.
Okay, and another question over here.
Wilson from University of Edinburgh. The hydrogen project looks very interesting, and you keep mentioning the ancillary service. And are you aware of any existing market you can trade this service with National Grid? Or you can depend on further development of some new market so you can trade this service with National Grid?
I'm sorry, I don't quite understand what it is you're asking.
Right, okay. Yeah, I mean, you got a wind farm there, and you're gonna use curtailment wind to convert to hydrogen and then store the hydrogen. At the moment, the National Grid pay the wind farm to give them some, payment to for the service of curtailing excess wind. And then you say you're gonna, convert this curtailed wind to storage, but convert the hydrogen and store in storage. Now, how this, the value stream, where you're gonna eventually, who gonna pay for this?
Yeah, I can't answer that at the moment. I'm sorry.
That's maybe a question for years 2 and 3 of this this
so.
PhD program.
Ask me next year.
Okay. Any more questions from the floor? Yeah. One more. Okay.
Question for Emily. Have you identified any, if we don't go for hydrogen as a security of supply, what would be the other technology in competition?
I think that's a bit outside of my scope as well at the minute. I'm sorry.
Okay. Any more questions before I do so? Yeah. Okay. One at the front here.
Hi, Paul Carey, University of Edinburgh. So this is quite a general question for this first speaker, because I don't know very much about heat networks. The thing I was wondering about was, with heat network, are you kind of reliant on the sources of the requirements for cooling and heating staying in kind of similar locations over long periods of time? So something like a supermarket, if it shuts down, suddenly you've lost all that cooling requirement, and then I don't know, is it still efficient to transfer the heat from a supermarket that's suddenly a lot further away from the houses that you used to be needing that heat from?
Thank you. Yeah, that's very right kind of observation in terms of what's happening if things change. And that could be something closing down, or it could be that we have different occupancy to what we're expecting. When we're designing it, we're designing for 100% in a flat, kind of in a building complex, but it could be 20%, or it could be delayed. It could be a lot of things. The answer to that is that as we are defining what our thermal zoning is, and by that I mean, do we put a heat pump on an individual house or an individual supermarket, or we put it a bit further back, serving quite a few units. When you have a district cooling or district heating network, you have a lot of different points of demand, and that way, because you have diversification, you kind of ensure that the whole thing is kind of balancing out so you can supply everything. As you're moving to this approach, which will be more decentralized, that's definitely a risk that you're taking. So a lot with the flexibility of having it in a more neighborhood approach, because it's really hard when you try to design for a whole city that you would be for a district heating or district cooling, you have that inherent risk with it. So there's a question of how do you mitigate against that, and in my opinion is that you plan your thermal zoning around that. So where you draw that line, that you put that energy unit is part of it. Does that answer the question? Amazing, thank you.
Okay. Anyone else have a question for our speakers? So I mean, I've just got a couple of questions for you, if you don't mind. So first of all, Orestes, on the sort of the kind of energy system side, or this district heating side. So there's a big kind of disparity at the moment between the amount of heat that we need and the amount of cooling. So is that potentially going to restrict the number of locations in which you can have this type of system? Because most of any kind of heating network or networks that we put in will be pretty much dominated by heating. So where do you see this being applicable, or do you think it would become more applicable as time goes on?
Yeah, that's true. And I think at the moment it's just the factor of 10. So I think heating is 10 times as much as cooling. But as we're looking into specifically urban centers, there's a lot of locations of wasted heat, and that could be the tube, that could be, for example, the sewers, that could be. So there's a lot of, that could be offices. So as we're moving to new kind of building, that we also have different consumer classes between an area, so not just residential, there's a lot of more sources and cooling demands that we would be seeing in other cases. That's definitely prevalent in more kind of Southern Europe, that we have both heating and cooling. But in London, for example, I think the scattered waste heat from low grade kind of low exergy or low temperature is more than the city's heat demand. So we could just be fueling everything through this. At the moment, we're just channeling everything to the atmosphere. So there is a lot of source of cooling. We're just not tapping into that aspect because of intricacies in the business model.
Okay, and this kind of follows on from the question we had from the floor about the sort of future-proofing or resilience of heat networks. So you've got this happening in parallel with a heat strategy that's looking to seriously improve the performance of buildings. So that's going to drop the heating load. It'll probably also drop the cooling loads as well. So if you have a quite significant reduction in heating and cooling demands, how does that impact on the economics of your heat network or your combined network?
Yeah, I mean that's one of the main issues right now with centralized networks, so district heating, because if you just have heating, for example, and as you're saying, your load drops, you don't have any revenues, and that is a proper issue with it. But when you have both the heating and cooling system, and when you rely on waste sources of heat, so you have a better balance from where you're drawing this heat rather than just generating it, you kind of have a lower operational cost. So your overall revenues end up adding up to more than it would be if you were just supplying heat. You're supplying heat and cool as a service, and it opens up a lot of opportunities because it's more of a neighborhood approach to maybe you don't have a monopoly of one energy supply company, but rather you could just have an energy community that is building the whole thing and it's owning some of the assets. And because you have a phased development of the decentralized energy substations, if one development comes in 2030 and another one in 2045, you have the ability to phase around it rather than putting all of the pipes and all the costs straight up from year zero.
Okay, thank you. That was a comprehensive answer. So Emily, just a couple of questions for you. So you showed a graph of the potential supply from wind when you get 30 gigawatts of it, and you also showed that demand with about a 4 gigawatt limit on it. What did that demand comprise of? Is that the current demand, or is that future demand with heating electrified and with potentially electric vehicles in there as well?
So the way the simulation works is that I use previous data, turn them into capacity factors, and then it gets scaled up based on like a specific area. So in this case, it was the 30 gigawatt of wind is what we used to scale everything. So the demand is scaled from last year's demand. I'm not 100% sure on exactly how it works because it's the computer that does it for me. I'm not 100% certain I can give you a 100% accurate answer.
Right. So I'm assuming there's going to be, in the coming years, some kind of QA of the data just to ensure that it's not realistic because it's the future, but just to ensure that the profiles that you're putting in would represent the scenario. Because obviously, if you start doing EV charging, you start introducing electrified heating, it totally changes the shape of the profile compared to what we've got at the moment. And again, I kind of just a kind of follow-in question. It's maybe a little bit cheeky, but when you're looking at the kind of interconnection between Scotland and England, and you're trying to kind of minimise that. Is that absolutely necessary? Do you need to have that drop down to zero? Because
not especially, no. Yeah. It's more just looking at how we can minimise the need for imports to make sure that Scotland by itself is energy secure. So the less you need imports, the more you're self-sustainable. You're reliant on the technology that is in Scotland and is readily available whenever Scotland needs it. So it's less about reducing it completely to zero and more about just minimizing it as like a cost basis kind of thing.
So, I mean, in terms of metrics, is that something you would continue to use, or will you be looking more at the potential for power systems problems later on down the line when you're doing your analysis?
Not sure.
Right.
Sorry.
Maybe a question for later on in the in the PhD again. Okay, so that's enough of me yakking on. So I'd like to thank our speakers for the presentations, both very, very interesting. So again, just a quick round of applause for them.